Swayam Prabha. Digital India. Educated India.
Very good morning, good afternoon, good evening, my dear friends. Welcome back to this 26th lecture for TQM under the NPTEL MOOC program. I am Raghunandan Sengupta from the IME department, IIT Kanpur. So, if you remember, we were discussing about the charts, the concept, even like I am going back about 2 or 3 lectures before. So, we had X bar charts and then the R charts, considering the concept. R, why we are using is the range when the standard deviation is not known, in case we want to replace R, which is the actual concept of dispersion or the overall variability which is there in the readings. If you want to measure them, obviously we need the standard deviation or the variance of the population, and if we want that, we will use the S charts. And we also saw that how, depending on the sample size, the coefficients of A1, B1, C1, D's would change accordingly from the tables, and we can use them accordingly. And if you are trying to eliminate or include more samples, how would the sample size have an effect on the coefficients would also be discussed later on also, and we have discussed it previously also with the change in the formulas, and we will continue discussing now in the 26th lecture, and so on and so forth. So, the charts and the processes for standard deviation estimation is, if you remember, we had changed the sample size, we have recalculated the mean value. Mean value can be either X bar charts for the X bar charts, bar line, sorry for the error, it would be the X double bar line as for the mean, and you have the upper control and the lower control, which we will use for the X bar charts, and then you will basically have the central line, which is the R bar for the R charts, and you have the upper control and lower control depending on that, and as the sample size change, you would have an effect on the X bar and the R charts also. So, continuing the discussion, we are trying to find out the actual central line or the upper control, lower control limit for the standard deviation estimation process. So, if it is the X control charts, here you had the concept of upper control and lower control given as 74.014, 73.988, and based on that you can find out where the fluctuation is, if at all, and then basically make very intelligent understanding of how the process is going, whether there are assignable causes, unassignable causes are there, and you can take actions accordingly. So, if you consider this chart, which I will highlight. So, in this region, if you consider there is a downward trend. So, I am using the highlighter only, and then if I use a different highlighter with the color, say for example green, so again there would be a change and it will go in upward trend. So, upward trend. So, you have to basically make an analysis that downward trend, upward trend, whether it is due to some causes or whether there is change in the overall workmanship. I am talking from the manufacturing perspective only, or there is a change in the quality of the raw materials, cutting tool has changed, or say for example the fluid which is being used for as the coolant has changed, whether the temperature in the room has changed, whether maintenance has been done on the machine, whether the humidity has changed. So, all these things would come into the picture. And if you consider the S chart, which is basically for the standard deviation, so obviously the trend would basically, that would give you the variability. So, here I will use another highlighter with the color blue. So, the whole trend is basically coming on an average in a straight line. So, that will give you that even if the means are fluctuating, the overall trend or the variability in the whole process is under control, because it is not deviating going over the upper control values. So, I will try to use the felt pen and with the color as red. So, any deviations which are happening above are not there, any deviations obviously they will not go below 0 is not there. In the same case, any movement upper the upper control limit, below the lower control limit are not there. Now, if I am considering the S square charts, S square is basically the best estimate, so called best estimate for the variance. So, what you have is basically the S, which is for the standard deviation, you will basically have the S square for the variance. Now, this S square can be of two types. Technically, when mean value is known, which is a tick mark, and mean value is not known. So, based on that you will do the calculation, and if I remember correctly, I did mention in the formulas as we are discussing that how you can find out the variance of the sample given the mean value known and variance of the sample when the mean value is not known. So, you have to basically use the formula in the first case as 1 by n, and the summation whatever it is, summation would be summation of xi minus mu whole square, and in the case when the mean value is not known, you would replace n by n minus 1, that means there is one loss of degree of freedom, and in the bracket inside the summation sign it will be xi minus x bar n whole square, because the mu has been replaced by x bar n, which is the best estimate. Anyway, continuing the discussion, so this S square chart is based on the sample variance. So, the upper control limit would be given by this. Now, this is the first time we are seeing this formula. So, I will highlight it using yellow color. So, this distribution we see here is basically known as the chi-square distribution. Now, the chi-square distribution, F distribution and T distribution, which I did mention a few times, are basically the sampling distribution which comes from the study related to something to do with the normal. So, technically we will use chi-square distribution when we have to study something related to the variance. We will use F distribution when we have something to study with the variance, but for two different populations, and when we are studying the T distribution or the Z distribution, we have to study something to do with the mean. So, if it is mean, it would be with depending on the assumptions, the distributions would be either Z, which is the standard normal distribution, or the T distribution, whatever the degrees of freedom they are, would be to do with the mean of the population, and chi-square and F would be to do with the variance, but in the chi-square case we are only concentrating on the variance of one population, and in F distribution whatever the degrees of freedoms are, it has to do something with the variance of two different populations. Now, if I remember, I did mention, and correct me if I am wrong, that in one of the classes previously I did mention that for the normal distribution, the sample mean and the sample variances are independent of each other, which is a very important characteristics for normal distribution. It is not true for the other distribution as such. So, in that case, if we consider, then the sample variance is distributed chi-square with a certain degrees of freedom. So, now where the chi-square is coming up, that will give you some information with my statement which I just made few seconds back. So, the chi-square distribution is coming. So, here where the chi-square is, so I will basically now highlight the degrees of freedom and the efficiency level of calculation. So, this degrees of freedom is basically n minus 1. Now, here let us take a pause. If you remember, I did mention in the part when the mean value is not known, you lose 1 degrees of freedom. So, this n minus 1 is basically coming from that fact that you have to use the set of observations x1 to xn the first time to find out something to do with the mean of the population, such that you use the sample mean to basically replace that. So, that is point 1, and point number 2 is that obviously if you are using that, you are trying to utilize the sample mean as the best estimate for the population mean, that is why it is n minus 1. So, in that case the central line would basically be S square, S dash or x bar is basically best estimate, and the corresponding upper and lower control limits would basically depend on what is the overall coverage area you are trying to basically cover. So, if you remember the value of the the overall efficiency or overall, say for example, degrees of freedom corresponding not to n, but basically with respect to the value of alpha which you are using. Alpha is basically the level of confidence which you have. So, if you are trying to basically understand that, then alpha would give you the exclude and include part which is there over and above the upper control limit and the lower control limit. So, this is I will basically try to highlight using the graph. So, let me try to do it. Say for example, I have this central line, this is the 0 value, this is the lower line, this is the upper line. So, lower line and upper line I am drawing randomly, I will come to that later on. Now, consider for the first time that I am trying to draw corresponding to the normal distribution. So, let me draw the normal distribution, let me change the color. So, this is the normal distribution which I have drawn. So, now if I consider the overall coverage in this area is 1 minus alpha. This is true for the fact that the areas which I am trying to cover on the left and right side these are of equal proportions because they are symmetric, hence the sum, if you consider, is basically 1. So, on the left hand side, right hand side, the overall coverages are alpha by 2, and the middle portion between the upper control and the lower control limit is 1 minus alpha. So, 1 minus alpha plus alpha by 2 plus alpha by 2 basically makes 1. Now, this was the true for the normal distribution case. Now, if I draw the chi-square, so let me try my level best to draw the chi-square. Let me again change the color. So, something like this. So, consider this chi-square. Now, the values which I will draw on the, so this coverage area would be basically be again equal to 1 minus alpha. So, this was 1 minus alpha, this also is 1 minus alpha. Now, I will try to use the color of green. This area and this area, they would add up to alpha, but in this case they are not equally distributed onto the left and the right side because this is not symmetric. So, that is why when I use the nomenclature of trying to mark, technically I will be using the concept that if I am reading from the left hand side, that means I have turned it vertical and I am basically reading it from the side where I am pointing my left hand. So, that is towards minus infinity, I mean coming to this side towards the mean value. So, the overall coverages would basically start increasing. So, if this total coverage is basically alpha by 2, so at this point the value should be such, whatever the chi-square value is, it would be such that the overall coverage area till that point is alpha by 2. Then I continue doing it. When I come to the next point, the overage coverage probability would be chi-square 1 minus alpha by 2, because I have already covered that area such that the area still left on to the right, which is this one, where I am now basically making it much bolder in green color. This area is still to be covered is alpha by 2. So, the overall area which I have already covered from minus infinity to that point is 1 minus alpha by 2. Hence, the nomenclature of trying to mention what is the chi-square, we use that nomenclature of the value of the degrees of freedom plus the level of confidence which is there corresponding to that point. So, if I now basically make a sense with the first set of diagram for the normal distribution, then it will be easier for us to understand. So, let me try to make the normal distribution in this slide only. So, the normal distribution which I am drawing is what I have already discussed. So, this is the technically I am just turned it anti-clockwise 90 degrees in order to make sense. This is the mean value, this is the z values which are there. Now, what is interesting to note is that this would be z alpha by 2 minus this would be plus z alpha by 2. Now, the interesting fact is these are symmetric. So, as they are symmetric, if you are covering z alpha by 2, technically the overall coverage from the left to that point and for z 1 minus alpha by 2 on to the right till infinity, the overall areas are same, which is alpha by 2. But the interesting fact is that they are symmetric because this is a normal distribution. Hence, we use in place of z 1 minus alpha by 2 you use plus, and in case of z alpha by 2 you use minus. So, this is the actual value only specific to the normal distribution, but the nomenclatures are as you are covering from the left, the alpha by 2 value or alpha 1 value, alpha 2, alpha 3 value, alpha 4 value or whatever it is the total area you have covered till that point. So, this has become a little bit too messy. So, what I will try to do is that I will try to remove this. Wait, just give me 2 minutes, let me remove this or else it becomes very untidy and it becomes very difficult for me to explain and for you to understand also. Yes, so it's cleaned, looks quite neat and clean, but even though I had covered a lot of concepts here, but we will come back to that later on. So, that technically the values of chi-square alpha by 2 n minus 1 would basically signify to from which direction you are coming and at that point what is the overall coverage is. Degrees of freedom again I am repeating is n minus 1 because I have lost 1 degrees of freedom based on the fact that I am trying to find out the sample mean as the best estimate for the population mean. Hence, it is 1 by n minus 1 when you are trying to find out the sample variance. The central line remains as s bar square, which is basically the average value of the samples. Now, if I go to the lower control limits, obviously this would depend, the degrees of freedom remain same. The overall coverage would now be based on the fact that whatever total coverages we have covered. So, that would be 1, this is the total area of the probability is 1 minus alpha by 2 because those that has been divided in that proportion that the central area covered is 1 minus alpha and the left and the right portion total sum of that is alpha by alpha obviously because that would be sum of them. In the normal case I am again repeating they are equal, so that is why I mentioned alpha by 2, but in the chi-square case it may not be equal because this is not a so called symmetric distribution, that is why I use the actual general nomenclature as mentioned. So, let me read the points again. I went a little bit slow trying to draw the diagrams, but please bear with me. The overall concept which I covered, if you actually go through it slowly, you will understand or refer to any good statistic books. These things would be made very clear in the book that how the general concept of chi-square T and F distribution are covered in a very simple manner. So, that once you fix in which direction you are trying to basically cover that probability and how you are going to mention the nomenclature of the names, things would become very easy. So, highlighting the bullet points, here S square is the average sample size, it should be S bar square as the average sample size, and this chi square which we denote. So, this is basically chi square which we are denoting refers to the chi square distribution with some degrees of freedom which is n. So, we basically have to look at the degrees of freedom. This charge has its limits defined in terms of the probability. So, that probability or level of coverage is basically the alpha value. So, if I am very much confidence, less confident, the values of alpha would be changing accordingly. So, moving range control, that means now the ranges, the average values change depending on the actual input data which is coming. Like say for example, in the morning 9 o'clock I took 10 readings, based on that I drew the charts. Say for example, at 11 o'clock in the morning I have taken another 10 readings. Now I want to basically include the first 5 and from the second reading, and include the last 5 from the first reading, excluding the first 5 of the first reading. So, this conglomeration of the new sample would be 5 from the first, that is the last 5 from the first, and the first 5 from the second one, and when we combine, obviously the overall mean value, upper control and lower control limits would change. So, obviously you have to make decisions accordingly. So, in many cases sample size used for process monitoring would be repeated. So, repeat measurements on the process differ only because of the laboratory on analysis on error, as there may be in, say for example, chemical process, manufacturing process, and all these different type of manufacturing process. The multiple measurements are taken on the same unit of product, such as measuring the oxide thickness of some process which is being done, or some paint thickness, or trying to basically find out the Young's modulus of a particular product, because you will be utilizing that for some designing the tie rod of a car, or trying to basically find out that how the trusses can be built for the bridge over a river. So, obviously you have to do multiple readings. So, in that case you need to basically find out the changing limits or upper control, lower control accordingly. So, continuing with what I am reading, such that as measuring the oxide thickness at several different locations on a wafer in a semiconductor manufacturing unit, because based on that you will be able to know that what type of connections would be needed, what is the voltage. Those voltage would be very small, but any small fluctuating in the voltage in the overall system on the computer, or say for example the laptop, or even the Android phone, would basically spoil the whole system. So, you have to be very careful what is the thickness and what is the voltage fluctuation, what is the ampere of currents which can flow, and all these things. In such situations, the control charge for individual units is useful. So, basically we use the moving range for 2 successive observations as the basis of estimating the process variability, and based on that we find out that how the range charts can be drawn. So, in this case, for the moving range you will basically find out the differences, the mod of the differences of 2 readings, 3 readings, 4 readings, depending on what you think at what stage the changes would apply, and use those mod of the readings, which is the mod of the range, in order to basically calculate how the R charts and the subsequent calculations can be done. So, in an example, let us continue. The mortgage loan processing unit of a bank monitors the cost of processing loan applications. The quantity tracked is the average weekly processing cost. So, you have a unit or set of officers who are doing that work. Now, obviously you have to pay their salary, there is processing cost, and so on and so forth. So, that is the weekly processing cost, or the yearly processing cost, or the multi processing cost, whatever it is. This is obtained by dividing the total weekly cost by the number of loans processed during the week. So, you process in 1 week 20, in another week 13, the next week 5. So, you have to find out the average cost on in the long run. The processing cost for most recent 20 weeks are shown in the table. So, the first column basically consists the weeks, the second column consists the cost, and the third column basically finds out the moving average range. So, in this case what we are trying to find out is the difference, mod of the difference. So, 310 and 288 is basically 22, then 289 and 297 is basically 9. So, you keep basically finding out the differences of those 2 consecutive values and basically find out the mod. So, it could have been, say for example, for 2 or 3 depending on type of readings you want to do. So, once we find out the moving average range, moving range, not the average, sorry, moving range, the average values corresponding to the second column, which is the cost, comes out to be about 300 point something. I am just hushing the decimal place, and for the moving range, the value comes out to be about 7.79. So, once you use that, depending on the calculations of the values of D2 you which will have, you will be basically be able to find out the central line, which is x bar, the upper control value and the lower control value. Now, again remember the value of 3 which is there here in both the upper control and the lower control would basically define the level of confidence you want for the upper value and the lower value. And if you go back to the fundamentally to the Z tables, you will find out these values of plus 3 minus 3 or plus 2 minus 2 or plus 1 minus 1 would basically signify the 6 sigma confidence, the 4 sigma confidence and the 2 sigma confidence level. So, obviously, you can take the values of that parameter, that coefficient which is 3 in these two calculations for the upper control level and the lower control level would be dictated accordingly. So, this is the charts which you have for the moving range. So, if you find out the moving range charts, so they give you the values accordingly. So, x bar is 300 and then upper control is 321 and the lower control limit is 279. Based on that, you do the calculations and find out whether the ranges are such that some of the readings are over the range or below the range, or where there is a particular trend based on which you can pass some actual conceptual judgment whether the process is under control or out of control, or whether there are assignable causes, unassignable causes, or whether the process has some variations which we are not able to notice, but which would definitely should take into consideration when trying to analyze the overall capability of the process. Now, as I did mention that for many of the cases the central limit theorem basically takes precedence. So, the normality of the readings, if they are not true, but we will consider that as we keep taking more and more observations in the long run, normality would basically be the deciding factor. So, based on that we are passing the next set of judgments which are normality assumptions before using the moving range chart is applicable, and they are as follows. If the process shows evidence of several even moderate departure from normality, the control limits calculated may be entirely inappropriate and we may not be able to use that accordingly. One approach is dealing with the problem of non-conformity would be to determine the control limits for the individual control charts based on the percentile of the correct underlying distribution. So, you will try to find out what is the correct distribution, and based on that you will try to find out that what the distribution you should use. Now, this you, as I mentioned that in the previous bullet point, is that if the variability for small changes is quite stark, then be rest assured the central limit theorem would not be holding true, and you have to basically use the actual central value, upper control, lower control value, depending on what is the actual distribution based on which you are trying to work. So, that is very important. So, if the variability is not much high due to not much of a change of like moving range values are not fluctuating much, variability is not that high, then be rest assured that central limit theorem would come into the picture and normality would hold true. I would say that rather than using the word central limit theorem, let me stick to the point that normality would hold true, and we are very assured that normal distribution characteristics can be utilized and we can do the calculation. But if the variability or ranges are fluctuating very high, then obviously it means that normality distribution per se does not hold, and you have to use the distributions as applicable for the cases for our study. So, this percentile could be obtained from the histogram if a large sample is there were available, or from a probability distribution fit of the data. So, that if we know what is the distribution, we are aware of its so called central value, which is the mean and the variability, and use those variance and the central values of the means to do the calculations. So, before plotting a MR chart, it is better to check for the normality assumptions for the distribution, and if we are assured the normality assumption holds true, then we can basically be rest assured that using those concept of normality would definitely give you much better results, or else you have to basically take the distribution as it is by drawing the histogram charts and the and the fitting of the best curve charts, and you will try to utilize those mean and those variances of that particular distribution for our calculation. With this, I will close the 26th lecture and continue the discussion in the 27th and onwards for the corresponding charts which we will consider later on in our course. Have a nice day. Thank you.